Good morning. I'm Córdova, Director of the National Science Foundation. I'd like to welcome our distinguished guests from the LIGO Scientific Collaboration, the Virgo Collaboration, and the Max Planck Institute. Members of the press, esteemed government officials, and scientists and representatives of ground and space-based observatories and supporting institutions from around the world. I'd like to specifically welcome Michael Kratsios, Deputy Assistant to the President and Deputy U.S. Chief Technology Officer, and Federico Farini, Director of the European Gravitational Observatory. Representing the National Science Board is Maria Zuber. We're delighted you all could join us for this event. In February 2016, we announced the first ever detection of gravitational waves, ripples in space-time, caused by the merger of two black holes in a binary system 1.3 billion light-years away. The detection, made by the National Science Foundation-supported Laser Interferometer Gravitational Wave Observatory, or LIGO, confirmed a major prediction of Albert Einstein's 1915 theory of general relativity and marked the beginning of a new field, gravitational wave astronomy. It also came decades after NSF and the National Science Board approved initial funding to Caltech and MIT to construct and operate LIGO. LIGO is an instrument so sensitive it can detect the smallest ripple in space-time, lasting only a fraction of a second. Gravitational waves can only be caused by the most spectacular cosmic events, as when one black hole collides with another. Following that first detection, scientists confirmed a few more detections of gravitational waves caused by colliding black holes, the most recent of which was in conjunction with Virgo. There is, of course, another event we were keen to detect. Today, we're thrilled to announce that scientists have detected gravitational waves coming from the collision of two neutron stars, the smallest and densest stars. This event occurred 130 million light-years from Earth in a galaxy far away. The LIGO detectors first picked up the signal. When Virgo did not see a signal of similar magnitude, it was clear the event was close to one of Virgo's blind spots. This enabled scientists to localize the potential origin of the signal more precisely, allowing ground and space-based telescopes, some 70 in all, to turn their attention there as well. What makes this discovery even more exciting is that scientists were also able to detect light, electromagnetic waves, from the collision. The very same cosmic event seen for the first time through multiple messengers, gravitational waves and electromagnetic waves. As an astrophysicist and someone whose passion for physics was first ignited by a television program on neutron stars, it's especially exciting for me to report on this rare event. Already it is transforming our understanding of the universe with a fresh narrative of the physics of stars in their death throes. The scientists who conceived of building LIGO and were primary drivers, Kip Thorne and Barry Barish of Caltech and Rainer Weiss of MIT, are receiving the 2017 Nobel Prize in Physics. Their vision and perseverance and NSF support made this discovery possible. This is what NSF does. We invest in high-risk, high-reward research that produces the discoveries that transform our world and advance the frontiers of knowledge. The benefits of these discoveries are not confined to the scientific community, but extend throughout the world, as discoveries from basic research coupled with novel engineering often do. Today's announcement should excite the scientists and non-scientists. It's a measure of what is possible when we have the courage to push beyond the limits of our knowledge and pursue answers to big questions. At this point, let me turn the program over to Dr. David Reitze. When we first announced the first gravitational wave discovery a year ago, David captured the excitement of the moment when he declared, "We did it." Well, Dave, we did it again.
Thank you, Dr. Córdova. Good morning, ladies and gentlemen. We have, for the first time, seen both gravitational waves and light from the collision of two dense dead stars called neutron stars. However, to do it this time, we joined forces with thousands of astronomers and many, many observatories. So we did it again, but this time we all did it. Let me start by telling you what we saw. The LIGO-Virgo network discovered two neutron stars colliding together. So LIGO is the LIGO Hanford and Livingston Observatory here in the United States. Virgo just started operating in August of this year. And we saw a signal at 8:41 a.m. Eastern Time on August 17th. The signal was much different from the black holes that we had detected before. It was much longer. And we analyzed this signal. And what we found was that it was a neutron star, approximately 1.6 solar masses, colliding with a second neutron star, approximately 1.1 solar masses, about 130 million years ago, 30 million light years away. So this graphic that you're seeing here is just the brief second where they collided. Now, this is a source that we always thought we would saw. Neutron star systems, binary neutron star systems have been predicted for decades, and we knew that we would see them. For me, what makes this event so amazing is what came next. The emission of light across the entire electromagnetic spectrum, revealed to us by a campaign involving 70 observatories, including 7 space-based observatories and every continent on the planet. So if you look at the graphic carefully that I'm showing, you'll even see there's a dot in Antarctica. So this is quite dramatic. This is an amazing, amazing discovery. And it was made possible by the fact that LIGO and Virgo, operating together, can identify the place in the sky where this event came from. It came from the southern hemisphere. It came from the Hydra constellation. So let me tell you a little bit about neutron stars. Neutron stars are very different from black holes. Now, they're produced from supernova, the explosion of massive stars. They're approximately 1 to 2 times the mass of the star. However, they're made up of pure neutrons. And the density of the neutrons in the neutron star is much, much greater than atomic nuclei, actually about a factor of 3 times greater. So consequently, they're very compact. Neutron stars are about 20 to 25 kilometers in diameter, and you can see in this graphic that I'm showing you the Bay Area in San Francisco. That peninsula is San Francisco. So what you're seeing there, to get a sense of this, is 1.5, 1.6 solar masses packed into a very, very compact region. So, all right, what does this really tell us? Well, astronomers have thought for a long time that the collisions of these neutron stars produce heavy elements, and there's been hints of that in other astronomical observations. But this result provides definitive evidence for the first time that elements such as platinum, gold, uranium are actually produced in these collisions. So I'm going to take out this is my great-grandfather's gold watch. It's about 100 years old. The gold in this watch was very likely produced in the collision of 2 neutron stars approximately billions of years ago. We don't know exactly when. So this is really an amazing discovery. You're going to hear today from the physicists and astronomers who participated in this remarkable discovery. In fact, the scientific story is so rich that it takes 2 panels to tell it. So you're going to hear from 2 different panels today. For me, the story is actually the big story is the fact that we're now using this new tool called gravitational wave astronomy, and we're combining it with traditional and very powerful electromagnetic astronomy to study the most powerful events and violent events in the universe. All right, so the analogy I'll give you is this is the first time the cosmos has provided for us what I would call a talking movie. We've moved from the era of silent movies to talking movies. In this case, the audio soundtrack comes from the chirp of the neutron stars as they are inspiraling, as they're orbiting together and colliding. And the video is basically the light that we see after the collision. Right, so before I step down, I actually want to also acknowledge that this kind of science does not happen without sustained support from agencies, and in our case, it's the National Science Foundation, which has steadfastly funded us for over 3 decades. And this is, again, another example of what I would call high-risk, high-reward science, where NSF swang for the fences scientifically back in the 80s, and we've yet again hit a home run. So I'm now going to call my friend and colleague David Shoemaker to the podium, and he's going to tell you a little bit about gravitational waves and how we detect them.
Thank you, Dave. I'm an instrument builder, and so I want to tell you a little bit about how these instruments actually can function. But first, let me say a bit about gravitational waves. Let's imagine you have a wave that's coming at you. The effect is to squeeze space along one axis and stretch it on the other, and then squeeze and pull in this direction. But space is incredibly stiff, and the result is that this event, some 130 million light years away, only made the smallest change you could imagine. If you had, for instance, a yardstick and the gravitational wave were to pass next to it, it would change length by less than a billionth of a trillionth of an inch. On the other hand, if you say, what's the change in distance to Alpha Centauri, some 4 light years away? It changed by the thickness of a human hair. So that's how small the effect is, and that's our measurement challenge. So one of the things, though, I just said is that you get a bigger effect if you go further away. The gravitational wave is a strain in space. It's like stretching a rubber band. And when you stretch a rubber band, let me get to the right film here. Good, there we are. When you make a longer baseline measurement, you have a signal which is larger. And that's why LIGO and Virgo have arms which are miles long to boost up the signal to the point where it can actually be measured. But you still need some of the most sensitive devices that have ever been made to have a sensitivity that suffices to get a measurable signal. You also need, critically, hundreds and hundreds of people who can design and build and install and run these instruments, and then thousands of people around the world in the LIGO and Virgo collaborations who then can analyze the data and get something useful out of it. So now we're going to look at a simulation of an interferometer. We use interferometry. We compare the peaks and troughs in light waves that travel down the 2 arms and then back together again. Now, between the peaks of the light we use is about a billionth of an inch. But in fact, we can split that down by another factor of a billion by using very powerful lasers. Really, it's the quantum effects of light that limit how well we can do. And with that, we can actually get to a signal that is immeasurable when the gravitational wave passes and shifts those wavefronts by a tiny amount. So software is constantly scanning the data that comes out of this interferometer and matching against hundreds of thousands of templates. We're looking for a match between what we see in the wiggles in the data and these different waveforms. The first time we saw this signal, it was in the Hanford detector up in Washington. That was where the signal was the cleanest and easiest to see. About that same time, though, we saw a gamma ray alert. Julie McEnery will tell you a bit more about this in just a minute. And that is a thing that made us realize that we were at a watershed moment for multi-messenger astronomy. We quickly put together a sky map that was based on the signals that we saw in Hanford, Livingston, and Virgo to form an idea of where this was in the sky and to give the astronomers a sense of where to look. That morning, I was talking with Laura Caudinanti about some rather boring bureaucratic matters that we're spokesperson and deputy spokesperson of the collaboration, and we were trying to figure out how we could get the collaboration to change its way of thinking for the post-detection era, when suddenly the phone alerts went off, and we immediately jumped over to the voice channel where all of the experts had gathered to try and understand where we were, and we shared in the joy and excitement of that moment. Now, while earlier detections of the black holes that we'd made, you can see it in the upper left-hand corner of this graphic, of this simulation, only lasted for us a couple of seconds or much less. This neutron star in spiral lasted for over a minute. And that's because these are lighter masses than the ones we've seen before. They're only about the mass of the sun, or 2 times the mass of the sun. And as a consequence, their frequencies are shifted up into a region which matches better the most optimal place in our instrument response function. And the result is that we can see the system for some 1,500 complete cycles of these 2 objects around each other. And it gives us a chance to get a very precise measure of the parameters of the system. But you have to imagine this. We've got these 2 objects, each one about the mass of the sun, but collapsed down to objects that are only 10 or 15 miles across, spinning around at close to the speed of light. That's a simulation, but that's what it sounds like also in the data. Spinning around at close to the speed of light so that they are eventually mixed together to make a single final object. It's an absolutely astonishing idea. We'll hear more about the fireworks that took place after the 2 fell together in terms of all the electromagnetic follow-up. Well, the resulting object and its electromagnetic radiation really is a treasure trove of information and is going to bleed, I think, for months or perhaps even years of study to understand better exactly what happened with these 2 objects. We don't actually know what happened to the objects at the end. We don't know whether it's a black hole or a neutron star, or perhaps something else. Some of the panelists later on will give some of the ideas of the evidence that they have for one choice or the other. Maybe some continued observation will lead to a really complete and final answer. Well, with that, I'd like to turn the podium over to Jo van den Brand. He's my opposite number in the Virgo collaboration, and he'll talk a bit about how we're able to point the astronomers to the right place in the sky. Jo.
Thank you, David. So the brand new European Virgo detector joined LIGO in the 2nd observation run in the month of August. We joined for 3.5 weeks, and it were the most spectacular weeks. It went beyond all our most optimistic expectations. So now we have a 3 detector network, and this allows us to localize the sources much better. So the gravitational wave first arrived in the Virgo detector. And then 22 milliseconds later, it was seen in the detector, LIGO's detector in Louisiana, and another 3 milliseconds later, it arrived in the Hanford detector in the state of Washington. So this allowed LIGO and Virgo to pinpoint the source of the signals to about 30 square degrees in the Hydra constellation. And this is by far the most precise sky localization of all gravitational wave events so far. So to get an impression about that, you see here the first binary black hole events detected by the 2 LIGO detectors only. And you see that the average sky localization, so projected on the sphere of the Earth, is about 1,000 square degrees. So now if you include Virgo, you get a global 3 detector network, and the sky localization dramatically improves. So this event was relatively close by. The SNR was the highest of all gravitational waves detected so far. So you might be surprised, why is the signal so low in Virgo? So now every detector has an antenna pattern, and that is shown on the slide there. And there are places in the sky, actually 4 spots indicated in dark, where the detectors are not very sensitive. Now you see also in the star where the source of gravitational waves was, and it was near a bright spot, near the most sensitive region of LIGO. On the other hand, in Virgo, the signal was hiding near a blind spot, and that explains why the signal was low. Still, the information in Virgo was sufficient to do the localization, and this allowed the follow-up studies to proceed. So with LIGO and Virgo, we could look at the source and identify these 2 neutron stars, and this was followed by a flash of high-energy radiation seen first by Fermi, and later also by Integral, and you see the common sky position indicated by the electromagnetic signals. So then you can look at the LIGO information. This is this circle on the sky, And combining that with Virgo, you see now that the gravitational waves point at the same sky location as you independently find from the gamma ray burst observatories. Now, if you look into that, then this region contains about billions of stars, about 50 galaxies, and it took a little bit over 10 hours for the astronomers to find the optical counterpart and the galaxy. So all this, I think, is an unprecedented demonstration of a global effort involving thousands of research universities and institutes and scientists, and looking all at the same single astrophysical phenomenon. With gravitational waves from LIGO and Virgo, we could see the source in fantastic detail, and then follow up by this flash of high energy radiation detected by the satellites. And then subsequently the source was studied in more detail by thousands of astronomers. The importance, the role of NSF was already pointed out, but I also would like to add that the realization of Virgo was possible because of the continued funding by both CNRS in France and by INFN in Italy, and later in the last decade followed by the Netherlands, by Hungary, Poland and Spain. So we did a lot of science, from fundamental physics to astronomy to astrophysics. We actually started right now on cosmology and nuclear physics. And I think this is a demonstration of what mankind can achieve if we put our minds to it and if we collaborate. So I think it's the start of a beautiful new field in science. And with that, I would like to hand over to Julie, who will talk about how Fermi saw the high energy radiation. Please.
Thank you. Gamma rays, the highest energy form of light, kicked off the light show. The gamma ray burst monitor on the Fermi Gamma Ray Space Telescope views the entire sky that is not blocked by the Earth. Around twice a day, we detect flashes of gamma rays. Flashes of gamma rays from thunderstorms, gamma rays from flares from our sun, outbursts of gamma rays from exotic stars in our galaxy. And important for the discussion here, a few hundred times a year, we see a brief flash of gamma rays from a gamma ray burst, a huge explosion in galaxies far away. August 17th started off as a perfectly normal morning for Fermi. We had breakfast. A gamma ray burst was detected, which by itself is not particularly surprising because we see quite a few of them. We saw a brief flash of gamma rays lasting just under 2 seconds. Half an hour later, we got an email from a colleague at Marshall Space Flight Center who works on both Fermi and LIGO saying, "Wake up!" in an email, which didn't actually wake us up, but okay. This burst has an interesting friend. And a few minutes later, we got a formal report from the LIGO and Virgo teams saying that they had detected a gravitational wave signal consistent with merging neutron stars just 1.7 seconds before the gamma ray burst detected by Fermi. And here I show the gravitational wave strain plot seen by LIGO. Half an hour later, we received another report from scientists working on Integral, a gamma ray observatory operated by the European Space Agency, who said that they had also seen the gamma ray burst. And with this started the most exciting morning of the 9-year Fermi mission. And the reason that this was so exciting is that there had been a long-held prediction that gamma ray bursts, these enormous explosions, that some of them, the ones that are short in duration, were powered by neutron star mergers. So within the first few minutes of getting this email, we realized that we had actually confirmed this prediction. So what do we think is going on? You've got two neutron stars that are spiraling around each other, spiraling closer and closer together as they lose energy by radiating gravitational waves. When they finally merge, they produce a huge energy release that powers jets that expand out into the material between the stars. We believe the gamma rays are produced in these jets. So this is great. We've solved a long-standing problem. But we're intrigued. In the Fermi detector, this looked like a perfectly normal gamma ray burst, just like any other short duration gamma ray burst that we see. But we knew from the gravitational waves that this burst was located more than 10 times closer than any other short burst with a measured distance. So it should have appeared very bright. So what's going on? One possibility is that we're not viewing this gamma ray burst down the barrel of the jet in the way that we usually do, but perhaps we're viewing it at an angle. Just as if you have a flashlight that dazzles you when you look straight at it, but if you're looking at an angle, it appears dimmer. With these observations, we're not just learning what happens when neutron stars collide. We're also learning something fundamental about the nature of the universe. The gravitational waves and the gamma rays traveled across the universe together for 130 million years and arrived within 2 seconds of one another. That's telling us that the gamma rays and the gravitational waves are both moving at the same speed, at the speed of light, as predicted by Einstein. So yet again, Einstein passes another test. So the story didn't stop there. The observations continued, revealing new and exciting features that the next speaker, Marica Branchesi, will tell you about. Thank you.
So Julie told you what Fermi saw in the sky, and I want to tell you what is the following story. So around 9 a.m. Eastern Time, about 90 group of astronomers around the world were alerted about the presence of the discovery of a gravitational wave signal coming from the coalescence of 2 neutron stars, 2 seconds before the gamma ray burst. A key moment happened about 4 hours later, when we sent the sky localization of the gravitational wave signal obtained with the LIGO and Virgo observatory. The sky localization was pretty good, and this source was close with respect to the other detected before. So a small universe and a nearby universe to be observed, a part of the universe where we know the galaxy. And at this point, all the observatory around the world start to look at the sky. And in particular, this source was located in the southern hemisphere, an ideal place for the Chilean telescope to look at that. And the Chilean telescope started to look at our sky localization at the twilight, and the first light escape has appeared as a very new bright object in one of these galaxies, NGC 4993, that is at the same distance of the gravitational wave source. We observed this object in all its colors, starting from gamma ray, then the blue ultraviolet light that fade rapidly and evolve in a red infrared object over a week. And then we discover also an X-ray emission and the radio emission after 9 days and after 16 days. This amazing discovery comes from a collaborative effort of different communities and 70 observatories that, including 100 instruments, they look at the same position of the sky for weeks. Each night observation brought a new piece to the puzzle to understand the neutron star and the engine that power light and sound. This is the start of the multi-messenger astronomy that allows us to hear the sound of the gravitational wave and at the same time to see the colors from the light. And the multi-messenger astronomy use different wave and different particles to observe the sky, also neutrinos. This time we didn't detect neutrinos, but we hope to add this messenger in our future observation. So the light in some band are expected also after years after the merger. And, but all is decided in a very small amount of time. When the two neutron stars dance around each other, became very, very close, about tenths millisecond before the merger, they start to feel tidal effect, tidal forces. And up to a few seconds after the merger, a matter is violently ejected in the interstellar medium. And this matter is the perfect site where heavy element can form. And the radioactive decay of this element powered the light that we saw in the blue, red, and near infrared. And this was predicted by the theories before. And we obtain amazing data, and some of them are, for example, from the telescope, the ESO VLTX shooter, Gemini, and the Hubble Space Telescope. And now I show you this data taken by the VLTX shooter. Here you can see a brightness decrease very, very rapid from the first to the second day. And from the third day, you can see in the spectra some broad feature that evolve. And these broad feature are the result of broad line blended together coming from this heavy element. So when the light escapes the matter, the universe is enriched by heavy element, and heavy element including also gold and platinum. So this, for the first time, we have observation that a large amount of these elements heavier than iron, form in this type of merger. And we learn a lot about neutron star and their life in the galaxy, and Vicky Kalogera will talk about this in the next talk.
Thank you, Marica. Ooh, fast. There we are. So what I would like to do in the next few minutes is tell you a little bit about the history of two neutron stars in a pair, and also the history of this particular discovery. So this is the first time that we hear the death spiral of two neutron stars, and we also see the fireworks that came from the final merger. But for decades, thanks to observations, astronomy observations in the radio wavelengths of light, we have known that pairs of neutron stars exist. It turns out that neutron stars are not just highly compact, as Dave Reitze already told us, but they are also acting as cosmic radio lighthouses. So they emit radio jets, and when those radio jets, as the neutron stars are spinning around their own axis, when those jets are crossing our radio telescopes here on the Earth, then we see radio pulses. So back in the late 60s, Jocelyn Bell Burnell and Tony Hewish discovered neutron stars as radio pulsating stars, pulsars, in our own galaxy. And we now know that many neutron stars actually appear as pulsars. And just a few years later, in 1974, Russell Hulse and Joe Taylor discovered the first ever actual pair of two neutron stars. One of them was actually observed as a pulsar. The other might be a pulsar, but for sure we knew it was a neutron star. And they were found in an orbit that radio observations allowed us to tell that the orbit was not stable, but the orbit was a spiral-in orbit. And the spiral-in was happening as fast as Einstein predicted it should happen, based on the emission of radiation of gravitational waves. It was the observation of this system that was discovered by Hulse and Taylor that actually provided the very first firm evidence that gravitational waves existed in nature. And it was this system that made gravitational wave astronomy a dream worth pursuing. In the Hulse-Taylor pulsar, we know that the two neutron stars are actually very far away from one another. They are over 1 million miles apart, 5 times the distance between the Earth and the Moon. And they will not merge for another 300 million years. But this discovery we are announcing today, when the two neutron stars entered and we could hear them with LIGO and Virgo, they were just 200 miles apart. And of course, more than about 100 seconds later, they merged. However, before their final 100 seconds, they had a long life together as a pair. And it turns out that before the second neutron star was formed in the system, it was the system, the progenitor of that pair of neutron stars, had a long, quiet life in its home galaxy. So it was going around its business, orbiting its own galaxy in a quiet orbit, the green orbit. It was green, the orbit in the galaxy, until the second neutron star was formed, and the system was kicked in the galaxy in the last phase of its life. And it was kicked in an orbit that allowed it to visit all kinds of neighborhoods in the galaxy. It went on a vacation at the last part of its life, touring all around, having new experiences all around the galaxy before the two neutron stars found their death together as a pair. And we can tell all of this by having the information from gravitational waves and electromagnetic waves. Now, what you see in the movie is that there's lots of little dots there. We haven't discovered lots of little mergers. We have seen one merger. But when we do our computer simulations, we cannot isolate a single orbit in the galaxy. We have a collection of orbits that are likely the history of this system in terms of its motion in the galaxy. So overall, I would like to highlight, as other speakers have done, that what's amazing with this discovery is that theoretically, all of this that was observed on August 17th was actually predicted. So over a century ago, Einstein predicted that two orbiting objects will emit gravitational waves as they spiral in. And astrophysicists predicted that as the two compact objects, especially neutron stars, collide, they should emit gamma rays in jets. And a cascade of light across the whole electromagnetic spectrum was predicted, and the production of heavy elements that might include gold and platinum should be produced. So it's amazing to think that in one day, in a few hours and the weeks that followed, all these predictions were confirmed. So we solved a lot of mysteries, but at the same time, we also opened up a few questions. As Julie said, not everything fits perfectly in the puzzle. So we're opening up a new set of questions. We're hoping that future observations that for sure are going to happen, both with LIGO Virgo, but also with our electromagnetic partners, are going to answer a lot of those questions. So the future for multi-messenger astronomy is definitely bright, and I might say golden bright. Thank you.
All right. Thank you to all our panelists, and we're now open for questions. Yes.
Seth Borenstein, the Associated Press. As Vicky just said, this was most of the things from the heavy elements, the art process, to the Hubble constant and gamma rays were all theorized in already and confirmed. What was the most surprising things you found, the new puzzles? What didn't fit that you now have to go and find, as opposed to what you confirmed?
So one thing was mentioned by Julie. Maybe she will elaborate. I mean, the faintness of the gamma rays, even though the source we know from the gravitational waves is so close by, is definitely a mystery. And I would say the delay probably in the X-rays might be a connected mystery, and you're going to hear a lot more about this from the second panel. And others may have something more to add.
Right. Another question, please? Here.
Yeah, so given the light activity
Could you identify yourself, please?
Yun Yu from Inside Science. So given the light activity that's predicted by the model during a neutron star merger, is there anything to gain, perhaps to implement some kind of automated system so that all the telescopes can point before even humans are aware of the event?
Yeah, that's Marica. Why don't you take that?
Yes, it's very important because, okay, this object was close and the region of the sky was small, and we expect more distant sources. We expect also to have a bit larger region of the sky to observe. So it's extremely important to have a robotic telescope that look at the sky continuously, and also automatic system to analyze the data and to remove all the contaminants, because we have transient objects in the sky, objects that appear and disappear, and some of them are very similar to the counterpart of gravitational wave signal. And so this is an extremely important part of this discovery.
Right, question here.
Hi, Sarah Kaplan from the Washington Post. You all have talked a lot about the significance of multi-messenger astronomy and how that's a big revolution. Can you talk about are there specific astrophysics questions that we're going to be able to answer now that we have these two messengers, particularly ones that readers who are maybe not physicists will be able to understand?
Let me try and take a crack at that. So another source that we would love to see, and that we would not only see in light and gravitational waves, but also in neutrinos, is a supernova explosion. All right. The problem with the supernova explosion is that we have to get really lucky, because they're very weak emitters. We can't see them outside our galaxy. They produce, tiny fractions of mass converted into gravitational wave energy. So they happen about once every 50 years. But certainly in the future, when we're running, we're going to be looking for that. And there are going to be more gravitational wave detectors that are coming online in the next 2 to 5 years, that when some of the detectors are down, some of them will still be running. So we'll hopefully still be able to capture them.
Can I add something to that, David? The other thing, if we collect more of these sources, these binary neutron stars, as we did so far, then we also can start getting into cosmology. So, for example, right now, already with this first event, we get sensitivity to the Hubble constant. And given our analysis, if we build up more of these events, we get more and more a handle on cosmological questions.
Right. Any other questions? All right, then we'll take a short break. I'm sorry, is there?
We have a number of questions from the...
Oh, okay, Lisa? Yeah.
Yes, thank you.
So this is questions from the webcast.
From the webcast, that's right. Rashmi Shivni asks, scientists saw signatures of recently synthesized heavy metals like gold and platinum, which basically solve the long mystery of where half of all the elements heavier than iron are produced. So, can we predict the frequency of these neutron star mergers events based on the proportion of heavy elements we see in the universe?
Try that one.
I'll try that one. So, actually, we can indeed attempt to do that. And one of the publications that is being released from the LIGO Virgo collaboration is attempting to do this kind of calculation. And I am sure I haven't seen all the publications that are being released today from our electromagnetic partners, so other colleagues might have attempted to answer that question. But I will say the following, that the question of how often these mergers happen is much better answered by the observation itself in gravitational waves. So not from the calculation of what's the quantity of these heavy elements we have. Because we have a high uncertainty for how much gold or platinum we're forming in each event. So the uncertainty associated with that is quite high. Instead, we know how long LIGO and Virgo have operated so far. And we know that we have detected one event, and we can calculate a rather tight constraint relatively to previous constraints. We have now a tighter constraint on how often these mergers happen. And just to give you an idea, these are very rare events. So with this one event, we can tell that in a galaxy like the Milky Way, our own galaxy, maybe they're happening somewhere between, very rough numbers, between 30 and 500 events in our galaxy per million years, okay? So don't hold your breath about a merger like this in our galaxy. The only way we could see one in a couple of years of LIGO operations, for example, is because LIGO and Virgo are listening to millions of galaxies, tens of millions of galaxies. And this is why we can get one in a couple of years, roughly speaking.
Okay, but it's a very good question, and the next panel may also shed some light on that. And I think it's going to keep theorists very busy working on that kind of question.
We have some more questions. With the merger of the two neutron stars and the kilonova, is the end state object a neutron star as well? And this question comes from Greg Redfern from WTOP Radio.
Okay, and I think David Shoemaker made some comments about this.
Say that we actually don't have any firm knowledge of what the final state is. There are some signs, you'll hear about this again in the next panel, some observations that have been made with the observation of X-rays that suggest that it should be a black hole. But in terms of its mass and all of the gravitational wave data, it could be either one of the heaviest neutron stars that's ever been seen or one of the very lightest black holes that's ever been seen. What we do hope, though, is that with a bit more observation, a bit more data, a bit more evolution of the source, that we'll have a more firm answer to that question.
Great. Another question from Camille Carsteel from Sky and Telescope. Are you able to say anything about the neutron star's equation of state, their radii?
Marica, you want to try that, or you want to give it to Vicky?
That the next panel will talk about this, and our gravitational wave data allow us to put some constraint on the equation of state and disfavor some type of equation of state, the stiffer one. And Laura Cadonati will talk about this in the bigger one in the next panel.
Here's another question from a freelancer, Meg Evans-Smith, who asks, what happens to the heavy elements that were produced during this collision?
Okay.
Who wants to?
Okay, I can say something.
Yeah, go ahead.
But I think that the second panel is the perfect one to answer all these questions. Okay. So this ejecta is spread in the universe. So from these elements that are spread in the universe, then you have also formation of other stars and propagate. And so what we have now, for example, in the Earth, is something that probably arrived from a merger of neutron star, and this dissemination of elements in the interstellar medium.
One more question. This is a question from Robert Kushner from Gordon and Betty Moore Foundation. What limits the sensitivity of LIGO today? What are you doing to improve it? This could raise the state of discovery from one a year to one a month. Then you'd really be an observatory.
Yes, yes. All right.
And we'd be tired.
Go for
What a great question.
We currently are not observing because, well, we ended our observing run on August 25th, and we're taking a year off now from observing to do just that, to improve the sensitivity of the instruments. All of the instruments, both the LIGO instruments and the Virgo instrument, were working at a fraction of the sensitivity for which they were designed. But it takes years of time to tune these instruments up to their full sensitivity. We expect to be able to increase the overall network sensitivity in this coming year of activity by about a factor of 2. That increases the distance to which we can see by a factor of 2, and thus the volume of space that's included by a factor of 8. The obvious answer to the question of what kinds of rates we could expect, something like 8 times as frequent signals as we've currently been seeing. So we might be going from one every couple of months to one every couple of weeks or one a week. The thing for which we have the best estimate of rates now, the question was posed before about binary neutron stars, is binary black holes. And so that's the kind of source that we're most sure that we'll be seeing at this greater rate. But I think all kinds of signals will come in more frequently. And ones that are nearby will come in with a signal-to-noise ratio that's a factor of 2 better, so that we can examine the waveform with even more precision and extract more information. So once again, the future is bright. We are going to have to talk a lot in our collaborations about how to deal with so many new events and so many new papers to write. It's a wonderful dilemma to have.
And also, we're looking forward to our colleagues in other countries developing their gravitational wave detectors, and then joining in the collaboration and increasing the positions of these sources and the detections of them. So, in addition to improving our current sensitivity of the detectors, we expect many more to join us in several years' time. So that concludes our questions. Thank you very much. And we will be starting the next panel at 11:15. Is that right? Is there any change in that? 11:15? Okay. All right. Any more questions before we take a break?
Hi, I'm Khan from the LA Times. Just a quick one. If these events are responsible for about half of the elements heavier than iron, what's responsible for the other half?
That's a good question. Marica?
So, many elements are formed in supernovae. So or when a star died. So the majority is supernovae. And supernovae were expected also to emit these, to form these heavy elements. It's more difficult, so the supernovae are more frequent with respect to the neutron star merger, but the amount of heavy element form are larger in this type of in the merger of two neutron stars.
Okay. All right. Well, thank you very much. And we have a really exciting panel of 10 observers from all over the world who caught this at various wavelengths coming up at 11:15, and they will fill in lots of the color and detail on this amazing observation. So thank you, and we'll conclude with the break right now.